Previous lesson, we looked at a network topology with 4 routers. There were no static routes added on each of these routers, and initially, each of these routers did not know about the networks that were behind any of the other routers. For example, R1 did not know about the networks 192.168.10.0, 40.0, or 30.0. Same thing for R2. It knew about 192.168.10.0, but it didn't know about 20.0, 30.0, and 40.0. Then what we did was we added 2 lines of config to each router. The first line started, it was these 2 lines here, router OSPF1, that starts a new OSPF process, and then we added this network statement. We'll look at the details of OSPF configuration in the next lesson, but for now, let's just recap what we did. So we added 2 lines of config, and after a while, we noticed new routes being added to the routing table on each router. In this lesson, we're going to take a look at that routing table after the OSPF adjacencies have been established. We'll discuss OSPF adjacencies in a future lesson, but for now, let's start by taking a look at the routing table. Before we open up any of the routing tables, let's recap all of the subnets that exist in this topology. There are 4/30 subnets, and those are the subnets between each pair of routers. So 10.0.0.0, 10.0.0.4, 0.8, and 0.12. And then there are 4/24 networks, 192.168.10.0, 20.0, 30.0, and 40.0. Once we've enabled OSPF, what we should expect to see is all 8 networks appear in the routing table of each of these routers. Let's confirm that. Let's start with R1. We will filter out the locally connected interfaces, and then let's take a look at these routing tables. So we see 10.0.0.0, 0.4, 0.8, 0.12, 192.168.10.0, 20.0, 30.0, and 40.0. The other thing that we want to note here is out of these 8 networks, if you look at each router is connected to 3 subnets in total. It's connected to 2/20 subnets and 1/24 subnet. That's the same for all 4 routers. So if you look at the routing table on R1, you see that it's directly connected to 2/30 networks and 1/24 network. And what it's learned through OSPF is about the other 2/20 networks and the other 3/24 networks. This should be the same on every single routing table. So let's just confirm that. Filter out the local interfaces, and we see 1, 2 directly connected /30 networks, 2/30 networks that are learned of through OSPF, 1 directly connected /24 network, and then 1, 2, 3/24 networks that R2 has learned of via OSPF. And that actually makes sense, because if you look at this router here, it's directly connected to 2/30 networks. It's learned about these 2/30 networks via OSPF, and it's learned about 1, 2, 3/24 networks via OSPF. Okay, you can pause this video to confirm that. The next thing that we want to look at is, let's look at the paths. Let's look at the actual routes. Let's start with R1 again. For R1 to get to this network 192.168.10.0, actually, before we talk about paths, let's just recap. All 4 routers here are the same model. They're the same routers, same models. All of the interfaces in this topology, they're all gigabit Ethernet interfaces. So there are no interfaces that are of a higher capacity, higher bandwidth than any of the other interfaces, right? So from our perspective, let's look at R1. So if R1 needs to get to the network 192.168.10.0, intuitively, we can say that the shortest path is to go directly to R2, and then we can get to this network. R1 can also get to 192.168.10.0 by going through R4, R3, and then to R2. But just looking at the diagram, we can tell that that's a longer path. So really, for R1, the shortest path to 192.168.10.0 should be through R2. you look at the routing table, we see that that is the case. We see 192.168.10.0, and the next hop is 10.0.0.1, which is this interface here. It's the same thing for the network, for the subnet 192.168.30.0. The shortest path should be through R4, even though there's another path, a longer path that goes through R2 and R3. If you look at the routing table, there is one path for 192.168.30.0. The next hop is 10.0.0.6, which is this interface. What about the network 192.168.40.0? R1 can get to this network by either going through R2 or going through R4. And intuitively, we can say that both paths are the same length or should have the same cost. And looking at the routing table, we see that that's the case. We see that for the network 192.168.40.0, there are two paths, 10.0.0.6 and 10.0.0.1. So from R1's perspective, it can send traffic down either of those two paths to get to 192.168.40.0 because each of those paths have the same length. We will discuss path length or path cost more accurately in a future lesson on OSPF costing. If we look at R2, we see the same thing. To get to 192.168.20.0, which is this network here, it just goes through 10.0.0.2, which is R1. To get to 40.0, which is this network here, it goes through 10.0.0.13, which is R3. But to get to 30.0, it can go either through R3, which is 10.0.0.13, or it can go through R1, which is 10.0.0.2, because both have the equal. They're both equally desirable in terms of routing traffic to 192.168.30.0. Another thing we can look at for each router, if you think about it, each router is connected directly to two other routers. So we would expect, intuitively again, we would expect to see two different next hops appear in the routing table. And yeah, we can confirm that. We see 10.0.0.2 as the next hop for some networks and 10.0.0.13 as the next hop for some other for other networks. And this is the same for every single router. Okay, so now let's consider something else. Again, remember, what we're still looking at is we're still trying to discover some of the advantages of dynamic routing protocols, and we're using OSPF as an example of a dynamic routing protocol to just understand some of the advantages that these protocols bring, that dynamic routing brings us. So what we'll look at now is, let's open up the routing table on R1, R2, and R4. Okay. All right. Now what we want to do is we will disconnect. Let's assume a link goes down. Let's say the link between R1 and R4 goes down. And we will do that by just disconnecting it physically. Let's see how the routing tables change. So right now, if we look at R1, there are two next hops, 10.0.0.6 and 10.0.0.1. Some traffic is going through R4 and some traffic will be routed through R2. Same thing for R2. Some traffic is routed through R1, some traffic is routed through R3. On R4, we'll see some traffic is routed through R1 and other traffic is routed through R3. Now let's go ahead and delete this. Okay. We see automatically the routing tables change, and the routing tables get updated automatically. Let's look at R1 now. R1 has lost 10.0.0.6 is no longer a next hop in R1's routing table, and that's because this link just does not exist. If we count the number of networks that appear in R1's routing table, so we see 3/30 networks, 10.0.0.0, 8, and 12, and they correspond to that 0, 8, and 12, and 10.0.0.4, which is the network here, no longer appears. We still see all four /24 networks, and that's because R1 can still get to this network this network here and this network here. But the path to get to all three of those networks is R2, which is 10.0.0.1. So again, if we take a look at this, to get to 192.168.10.0, the path is 10.0.0.1. To get to 20.0, it's directly connected. To get to 30.0, which is the network there, the next hop is still 10.0.0.1. And to get to 40.0, then the next hop is also 10.0.0.1. So essentially on R1, we can still route to all the networks that are, all the subnets that are up, but the next hop is only through 10.0.0.1, which is R2. On R4, it's exactly the same. We see only one next hop in the routing table, and that's 10.0.0.10, and that's because all the traffic has to be routed through R3 since the link to R1 is down. We still see all 4/24 networks. It's just that they're now all going through R3, 10.0.0.10. And we see all 3/30 networks that are still up. If we look at R2, R2 still has two next hops in its routing table, and that's because the link to R1 is up and the link to R3 is up. So to go to 192.168.20.0, R2 will go through, so 20.0, R2 will go through 10.0.0.2, which is R1. But for every other network, R2 is going to go through R3. So to get to this subnet, and this subnet, R2 is going to choose R3. So 10.0.0.8, which is this subnet, 192.168.30.0, which is this subnet, and 192.168.40.0, which is this subnet. For all those three subnets, R2 is going to send traffic this way. But the key thing to remember here is that we disconnected one of the links. We didn't have to make any changes. The routing table is automatically updated to reflect the change. Now, what happens if we bring this link back up? So let's connect this link again. Okay. The first thing that happened is we noticed that the routing table changed. So what changed? This 10.0.0.8 network is now back it appears back in the routing tables of all four routers. So we see this network. What hasn't changed yet is on R1, we still see only one next hop. On R4, we still see only one next hop. And the reason for that is it takes some time. These two routers had lost their OSPF adjacency. So it takes some time for that adjacency to be built up again. And like I said, we're going to cover adjacencies in a future lesson. But once those adjacencies have been built up, and now you see, now you'll see slowly the routing tables update. Yeah, and there you go. You see two different next hops, 10.0.0.6 and 10.0.0.1. And just to confirm, to get to 30.0, the next hop is 10.0.0.6. And to get to 40.0, which is this network here, there are two next hops, 0.1 and 0.6. R4's routing table has updated to reflect the same thing. R2's routing table has updated to reflect the same thing. I'm going to show you the routing table for R3 as well. Feel free to pause the video at this point and inspect each of the routing tables. Okay, so now let's look at one more thing. We'll close these routing tables. The next thing is okay, let's see. Okay, yeah, the next thing we're going to look at is, let's see what happens if one of these networks goes down. So let's bring up the routing table then. R1 and R2 and R3 again. Okay, so these are the routing tables on R1, R2, R3. On R4, well, let's do this on switch 4. Or even better, let's just delete this interface. Okay, so we've deleted that interface. So now the subnet 192.168.30.0 should no longer be available. And if you look at the routing table on every single router, it's gone. So there's no 192.168.30.0 in R1's routing table. It doesn't exist in R2's routing table. It doesn't exist in R3's routing table. Again, we had to do no manual configuration required. As soon as that link went down, all the routing tables updated automatically. We can connect this back up again. And again, automatically the route reappears in the routing tables of all the routers. How about, let's look at another use case. How about adding a new network or a new subnet behind any of these routers? Let's do that with R4. So what we're going to do with R4 is we're just going to, if you look at the config, on R4, GI02 has this IP address, right? Which is that network there. What we're going to do is we're going to add a new sub-interface. So let's create 02.31 encapsulation.1 Q31. So we have to give it a VLAN ID. And now we assign an IP address 192.168.31.1 255.255.255.0. Let me just move this up here so that you can see the routing tables update automatically. Okay, I hit enter, and right away we see 192.168.31.0 appear on the routing table here, here, and here. If I do a no shut on this interface, if I shut down this interface, it disappears from all the routing tables. 31.0 no longer exists. I do a no shut, it's back up. If we want to just confirm that we can route from here, we can add another computer. We also need to modify the configuration on the switch. So let's start by adding the VLAN. Then we go to interface GI03, assign it to VLAN 31. We go to interface GI01 and convert it to trunk mode. Trunk. Let's just confirm that the VLAN's there. VLAN 31 is on GI01 and 03. Okay, should be good to go. We're now going to come in here and assign this an IP address from VLAN 31. The default gateway is the IP address of R4's interface GI02.31.1. Okay. So now we should be able to ping any of the other computers from this through BCE. Let's try 20.2 and 10.2. Okay, 20.2 works. 10.2 works. And 40.2, which is down here. This subnet here should also work. Or rather, it was this PC here. Okay, so let's recap what we did in this lesson so far. So we started out by inspecting the routing tables on each of the routers after all the OSPF adjacencies were established. What we noticed was that in each router in its routing table had a total of 8 subnets. 4 of them were /30s and 4 of them were /24s. Out of those 8 subnets, 2 of the /30s were directly connected and 2 were learned from OSPF. 1 of the /24s was directly connected. The other 3 were learned through OSPF. We also noticed that in the way OSPF installed the paths in the routing table, it would always install the shortest path first. If there were multiple paths that were both the equal length, let's use the term length for the purpose of this lesson, they were both installed in all of the paths of equal length were installed in the routing table. If a link went down, so we tested that by removing this link, the routing tables automatically updated so that each router was still able to route traffic to all of the 192.168/24 networks, but the next hops were modified because only one path was available. We also saw that if we removed any one of these networks, so for example, removing 192.168, this 40. Network or this 30. Network would automatically remove that network from the routing tables of all the routers. And the last thing we did was we added a new subnet behind one of the routers, and we saw it automatically populate the routing table. We automatically saw it update the routing table on the remaining routers so that this new subnet was reachable from everywhere on the network. So to recap, what we saw was simply by adding 2 lines of configuration on each router, we made this network much more resilient and scalable, because we could now add and remove networks from any one router and not have to touch the configuration on any of the other routers in order to reflect those changes. Conversely, if this had been a statically routed network, if we were only using static routes, every time we made a change, we would have to change the static routes in every single router. So you can see why dynamic routing protocols such as OSPF can provide a lot of benefit when we're managing routes in a large network. So the first 2 lessons covered some of the advantages of protocols like OSPF. In the next lesson, we're going to look at the OSPF configuration in a little bit more detail. We will look at these 2 commands that we entered here in a little bit more detail.